Building science is really an intimidating subject to a lot of architects, builders, or people that are working in the construction field. One of my favorite sayings from Joe Stiebrick really feels like it's all you need to know about building science, and that is water forms when warm air hits a cold surface. And that literally is, when it comes to building science and designing a thermal envelope, everything that we do and work towards is really directly related to that simple statement, whether it's happening on a micro level or in a serious level. So it really does have significant impact on your durability of a building, and it really can make the difference, like between a building lasting 7 years and a building lasting 100 years. As well as, poor building science is generally responsible for a huge amount of cosmetic damage that happens during a building's life cycle, just dirt building up on walls on the interior, your sills, like paint cracking around your window sills, or paint falling away or delaminating around other mechanical penetrations. Or people think that typically those are roof leaks, or a lot of times that is just building science in action. Again, when warm air hits a cold surface, water forms. And so we're going to talk about why, how that shows up in our prescriptive code, what code is doing to address that, and then how B.PUBLIC addresses it as we shift to a fully vapor open wall assembly. And we can see why that's so critical for durability when it comes to thermal envelope design. So this is a poor drawing nonetheless of a typical conventional prescriptive code. So here on wall assembly, so here on the inside we have our sheetrock. And then we have our electrical box or light switch junction, typical. And then we have our cavity insulation, and this could be, most commonly it's fiberglass. In this case, we're gonna presume it's fiberglass. And then we have our exterior sheathing right here. A lot of times that's what's showing up in a wall assembly. And what current codes are moving towards now, or current prescriptive codes, is they're now specifying, and they've been doing this on commercial buildings for a while, but they're specifying then a continuous rigid insulation on the exterior. And so, and the reason is that, this is considered our air barrier, this sheetrock and so forth. So, but the issue is that, of course, J boxes and so forth, they are not airtight. And so on the inside of the assembly, we have warm air from cooking, showering, us heating, heating up the interior environment. So that warm air, and it's relatively moist, but again, even if it's warm, it has such a huge potential for carrying moisture compared to if it was cold. So just by the nature of it being conditioned air really makes it moist in this scenario. So that moist air, warm air, travels through leaks in the sheetrock and so forth. And again, as we talked about before in some of previous sessions, this fiberglass doesn't really resist any airflow. It has a tremendous, you can just blow air through fiberglass. So it has a great performance in conduction, but really poor performance in convection. So air is able to move through it. So as that warm air moves through it, because fiberglass isn't able to absorb moisture, if it's a little bit cold as it's getting to the exterior of the wall, droplets start to form. So what did we learn? That warm air hitting a cold surface, water forms. So that water droplets start forming on this fiberglass. And fiberglass will tend to clump when that happens. If anybody has opened up a wall, a 50-year-old frame, wall from the 20s or 50s, what you'll see is that, the backer paper for the fiberglass insulation, but there's no insulation on that backer paper. It's all at the bottom of the wall cavity. And that is due to that clumping, moisture clumping that fiberglass insulation and it failing and falling down. And so that's the impact that it has to that fiberglass. Even more critical is that as that warm air keeps on moving through, it hits the back of our sheathing right here. And if we don't have this rigid insulation on the back side, it's hitting that dew point effectively. So warm air hitting a cold surface, the back of that plywood or OSB, and it condenses right there at that point. And so that's where we tend to get a tremendous amount of decay and rot. And again, it's happening at a lot of times where that higher airflow is coming out. So it would be joints and leaks in that exterior sheathing. So right where it's, most critical, where we have joints in that sheetrock and so with that, or in that plywood, that's where we're going to have decay occurring. And so current codes are really trying to address that. Unfortunately, not by trying to address some of the building science or through preventative measures out here, but more as sort of reactionary. So specifying rigid insulation on the outside that is stopping or reducing that dew point so that it's not condensing as much on that surface. But still, you have a tremendous amount of convection happening in this assembly. So even if it's not happening here, it's coming out through your top plates and so forth. So there's pretty rapid decay in relatively within this wall assembly. And so going over to the typical B.PUBLIC assembly, there's a couple sort of notable differences. And a really big one is just the commitment and dedication to a single and continuous vapor control layer, which is also the air barrier. So by having it here on the back of what we see this as a service cavity, so instead of having the receptacle, penetrating what is considered the air barrier, putting that receptacle in front of it on the warm side of it. So now you don't have to worry about any penetrations within that interior finish. This could be wood slats or anything like that. It's not going to have any impact on your overall performance or durability of your assembly. And so that's really big, because then again, as we have warm air on this side and it's coming through, this air barrier and the vapor control layer is just really limiting how much air from this side can get over to here. So even if this is still, say, warm on this side and it's colder on this side, this air is not mixing between them and the vapor is not going back and forth between them. So the relative humidity within this space is so much lower compared to the relative humidity on the warm side. And so once we've done that, then there's a couple things that we do to make that, I think, even more robust or resilient across different climate conditions. And that is, instead of using fiberglass, we're using cellulose insulation. Since cellulose is a natural fiber, and again, it has a lot of capacity for actually absorbing moisture, opposed to it creating condensation and clumping the insulation, that the cellulose can actually absorb a little bit of that moisture as much as it needs to and then releases it again. So it's very vapor open, so it doesn't harm it at all to increase its relative humidity within the expectations that we have within a wall assembly, and then it just releases it over time. Say even if it's 6 months later, it's doing it very slowly, but it's not ever building up to a point where it's causing any harm. And we talked about it before around that this is a vapor open assembly, so even as we get to the exterior of our sheathing, which it might be the same, this is plywood, but because we have a vapor open exterior weather barrier, that moisture is able to leave considerably, but we don't have nearly the condensation that would occur on this assembly because we've controlled it on the interior. And this talking about vapor open too. This is one of the aspects that we don't like about the prescriptive response to building science in this way, is that typically these are rigid insulations, so EPS, XPS, so higher carbon footprint, petroleum-based rigid insulations, but they're also totally vapor closed, so no moisture is able to get out that way. And so all of this wall has to dry to the inside, which is a little bit more difficult for that wall assembly to do on a full annual basis, opposed to a vapor open assembly where this is your tightest point and the wall is drying out on both sides from it. So it just makes it extremely robust from a health perspective as well as climate perspective. And so it can deal with, Chicago winters and Chicago summers for that matter. So a little bit of building science one-on-one. Again, really, it's such a good rule of thumb that when warm air hits a cold surface, water forms.